I guess I can start with just a little bit about me. I was interested in neural networks since when I was in university. I first basically started experimenting with convolutional neural networks, and I was incredibly impressed that even the mistakes it was making, it was mistakes that I could have made. But back then, that was not very popular now. It's only in the last like 10 years that it's been picking up. So I briefly went into like aerospace with flight simulators. Then we started a startup trying to extract data from receipts and provide receipt solution. And I'm currently working with Sensibill, building receipt products with deep neural networks. So first, I would like to talk a little bit about the principles behind deep learning, which is more than basically stacking a bunch of layers together. The main principle with deep learning is that we'll learn from raw data. So instead of using pre-processing techniques, trying to change the data into bringing it into familiar forms, the idea with deep learning is that we don't want to design these handcrafted features that we have to basically redesign every time we switch domains. So we have different features, extractors for sound, different ones from images, and whatever new problems come, most of the research that's done is in trying to do these feature extractions and then feed it to one of the existing machine learning techniques. So the idea here is that we don't want to do this pre-processing. We just want to feed the raw data as is, possibly, and let the machine figure out what are the most important things and what are the regularities in the data that needs to be extracted. And also use general purpose architectures. So eventually, where this deep learning field is going is in building true artificial intelligence, general intelligence. So that's why a lot of research is going into algorithms that are not specific to the data types that we're trying to process, but work in general. So the same algorithm could work for images, could work for text, could work for sound. We just need to basically do a preliminary pre-process to just transform the data into numbers, because that's what the neural nets just know, numbers. And then we would just use the same neural net for analyzing sound and analyzing images. And the way we achieve that with deep learning is we use this multi-layer approach. So at the beginning, you have the raw data that feeds into the input layer. And then the input layer learns how to extract some higher level features from that. And then we can repeat the process by adding more layers to extract higher and higher level of information, so that at the end, it can basically get classified or whatever the task it is that you want to make out of that. So just to get basically an idea of the whole evolution of this field, I wanted to include a little bit of history, especially because only the recent 10 years are known about this deep learning field, and it seems like it came out of nowhere. But actually, there's been decades of research that only currently crystallized into a proper field, and all the companies pick them up, and now it's this new craze of deep learning. So, sorry. We can consider the father of deep learning, Ivan Henko, which is a Ukrainian, I believe, scientist. Since 1965, he started experimenting with this multi-layer idea. Now, back then, he didn't have this backpropagation that we use now to train our models. He had this similar looking to neurons units, and he would use this regression analysis to train each layer at a time. And then he would have another technique to basically reduce the number of parameters, to figure out what are the parameters that are not really doing too much work, and kind of keep pruning these layers. And eventually, if the one layer was not good enough, he would add another layer on top, repeat the process until he would get the good accuracy that he wanted. So, and he actually, his nets were not technically neural networks, but his networks were used up until the new century, and they went up to 8 layers since back then. So a bit later on, first the backpropagation algorithm that now it's used to train all kinds of neural networks. They're all trained with backpropagation. And then they basically came out of control theory. So first, Bryson and Kelly, they were using continuous signals. So the idea is that you take the output of your network, of whatever the machine is, then you also have what you want the machine to produce for that current input. And then you make some difference. You create this error measure between the actual output and the ideal output that you wanted to produce. And then the backpropagation algorithm is the way to figure out how to change your parameters so that next time your output to the network would be closer to the desired output. So they first started applying it into control theory in the continuous case. Then there was a later research, Linda Inma, who started coming up with a backpropagation in the continuous space. And then eventually the first one to apply backpropagation to neural networks was Paul Werbus in 1974, where he basically was using the modern technique of backpropagation that we're using today. So we can see that since 1974, we basically had all the components. We had the neuron models, the backpropagation techniques on how to train this idea of the layered process. So it's been decades that all the main components were there. And then the first, initially, neural networks were used in this formation of multi-layer perceptron, which is the diagram over there. So basically, it's the same principle that I explained before, that you have layers of neurons. These are artificial neurons that are basically modeled by the model of the actual neuron. We have we have the input layer, and then we would feed that to multiple layers to get to the output layer. And so initially, this was sort of the main architecture that was used with neural networks. But the problem was that you couldn't really add too many layers. It was not really known at the time, but if you kept adding layers, you didn't get any good results. So therefore, you couldn't really use this as a deep learning network that we're used to now. So people tried with, for example, character optical recognition, or trying to feed basically the raw pixels. So in the input layer, if the X is there, it could be just the pixel values directly. And then you can add layers, and then trying to do, say, like an image recognition task, that just wouldn't work. So more and more, the research started happening into this feature extractor. So the idea is that you take your raw data, you feed them through some handcrafted, most of the time, algorithm to extract your features, and then you feed your feature vectors to this multi-layer perceptron, and that will basically give you the output that you want, which would be, say, in the case of an image classifier, would be the class of the object. The problem with this was that now the work kind of shifted from the actual neural network to designing these feature extractors. And this didn't really solve the problem because it just moved the complexity to these feature extractors. And that was the reason why neural networks for a long time, I mean, since '74 until the '90s, no one was really talking about neural networks. It came to a point where if you had neural networks in your paper, it would just automatically get rejected. And that was, well, there was, I guess, historical reasons for that. There was people who basically been working on feature extractors for a long time, and there was other alternatives. Instead of using the multi-layer perceptron, you can use like a support vector machine or other different techniques that at the time with the computation power, they were basically getting better or equivalent results. So a lot of researchers basically started to move away from neural networks. Despite the initial hype. So there was the first revolution when backpropagation came. There was some good theories that came out of that. It was basically shown that if there is a set of parameters that can solve the problem, this algorithm is guaranteed to find the solution. But the problem was that for real problems, like say an image classification task, this set of parameters doesn't exist. So you have to do this feature extractor. There was still a few sort of brave researchers, you could probably count them with one hand or all around the world, who continue to research in this neural network field. So basically their thinking was, okay, fine, like we can't have just this simple multi-layer perceptron to solve our problems, but we can work with how to extract features with neural networks in an automatic way. So we basically have to find better architectures in doing this feature extractor. So one of the other revolutions, which was basically the rebirth of this whole neural network field, was the convolutional neural networks. They are now becoming very popular. They came from previous research. So the initial model of this convolutional neural network was based on biology. So here comes biology again. First, we had our model of the neuron based on our own biological neuron. Now they started using even architectures that were based on the architecture of our brain. So with a project, LeCun, for example, in 1989, he showed that first of all, he built a data set. So I guess the drawback of these deep learning techniques is that the data sets that you need to have, they need to be a lot bigger. Because before, with this feature extraction, we were putting domain knowledge into the problem. So I know, for example, how characters look, so I can handcraft algorithms to design features about how characters look, and so on, or images and so on. But with a deep learning approach, there's no domain knowledge being input into the system. So the training set you need is it needs to be usually a lot bigger. So what LeCun did, he first started experimenting with optical character recognition with handwritten digits. So the printed digits was pretty much already pretty good because printed characters are sort of fit a template. You can kind of design handcrafted solutions to try to get that. But handwritten digits are already a higher level of complexity. So what LeCun did, it took an existing data set of handwritten characters, which was the NIST, and then he modified it to come up with an MNIST, which is now one of the most popular data sets. It's used as a benchmark for all kinds of algorithms. So LeCun was basically the first one to show really good results with convolutional neural networks. And he could show that there's all these different advantages to using convolutional networks, and then he started to apply that into other domains like sound, different classification tasks, and basically he was able to beat different algorithms that were domain specific, so they were designed specifically for different problems. He was able to beat those benchmarks with the same architecture. So that was sort of the first sign that this is really, there's something big behind this. But even then, they were mainly ignored by the academic community. It was until all these researchers started to get picked up by private companies, and that's where there was more attention into this field. And then, so first it was this MNIST data set with the characters, and then they started to apply it into harder problems like image classification, object detection, where there was no really good solution for it. No one could tell the difference between a cat and a dog. Before, it was with convolutional neural networks, because the problem is, how do you describe this kind of a difference? In the classical approach, you have to describe all the steps of your algorithm to basically come up with a solution. But I can challenge anyone to give me sort of some rules on where does a cat look different from a dog, and you'll have a lot of trouble with that. So by using convolutional networks, we don't have to have the domain knowledge. We just feed the images. We feed in what is the actual label that we wanted to produce, and the network will learn by itself to produce the correct output. So now this has been extended to thousands of classics of objects that is in this specific domains is actually performing even better than humans. In this image classification, there was another project for example, for reading road signs that are used by self-driving cars that outperforms the people's ability to read this road sign. So we're already starting to see in specific domains these networks starting to basically beat human performance. So just I want to talk a little bit about how these convolutional neural networks work. So the idea is still this multi-layer idea, but what the convolutional networks do, they try to reuse a lot of these parameters. So the idea, the multi-layer perceptron, it just takes, in this problem of image recognition, we would just take all the raw pixels and feed it, all of them to the next layer, because the layers in between them, they're fully connected. So each unit in a previous layer sees all of the image. But the insight came from the neocortex. So this model comes almost straight from biology books, where they did experiments with cats, I think it was, where they would probe into the neocortex of the cat and then try to see what kind of neurons get excited when you present different images to the cat. So there's this known layered approach that the cortex has. It's not like fully layered, but you can kind of tell this layered in the cortex. So they would see that in the lower layers, they could find neurons that respond to lines of different directions, for example, different colors, so very simple patterns. If you probe a little bit higher, you'd see a bit more complicated patterns. So you could see simple shapes like squares, circles, and so on. If you probe a bit even higher, you see even more complicated. And if you probe on the top layer, you could recognize higher level objects. Like, for example, the famous Bill Clinton neuron. Some researchers found this neuron that every time that person saw a picture of Bill Clinton, this neuron will spike. So this neuron was named the Bill Clinton neuron. which kind of is not really about Bill Clinton. It just shows that in this high level of cortex, you have neurons that respond to high level things like a human face. So this is the principle that is applied over here. The way we do it is doing through this convolution. So if you're not familiar with the mathematical term, convolution is basically a filtering operation. You have this small kernel. You can think of it as a small window, and then you apply that same kernel on all positions of your image, and this effectively generates a map. So we can treat this kernel as a feature, and the result of the convolution is the feature map, which tells you basically where is this feature in the image. And so basically now we're reusing these weights. This layer now, they're not fully connected anymore. Each of these layers sees, basically each of these locations is sharing the parameters. So with one sample, we can get a lot more training out of that because it gets repeated throughout the whole images. And the same principle gets applied multiple times to multiple layers until you reach a small enough representation. Then you can use that to feed that straight up to multi-layer perceptron. So, sorry, it's getting trigger happy. So if you look there in the image, all this maps is basically the convolutional layer. And at the end, the last part over there is the multi-layer perceptron that we had before. So what we did here is basically we replaced those handcrafted feature extractors with another neural network that does the feature extraction. And then we feed everything to the multi-layer perceptron to produce the final outputs. This had tremendous success. But it was clear that sort of something was still missing, theoretically. Because if you try to solve more complicated problems, keep adding more layers, the learning would not happen. So just like with the multi-layer perceptrons, this layering approach could not keep going forever. After a while, you couldn't learn. Now, it was not fully understood at that time, but the problem was a fundamental one. It was a fundamental problem with deep learning. So, as it turns out, it was actually sort of mathematically understood by Sepp Hochreiter in the Swiss AI lab. Out of that analysis, he came up with a mathematical understanding of this deep learning problem, which is basically the vanishing or exploding gradients. So the gradients are these signals that are propagating backwards to the network. As I said before, we feed an input to the network, and this is the forward propagation path that produces the output. And then we take the output and the ideal output that we want to produce, and then through this backpropagation algorithm, we feed, there's a signal that feeds backwards all the way to the input. The problem with this is that this gradient, so this signal that's going backwards to the system, is exponentially changing. So if you know the nature of the exponential, depending on the base, if it's greater than 1, it can explode to infinity. It can go to infinity. If it's smaller than 1, it can go to 0. So we're basically seeing the problem of exploding gradient and vanishing gradient. As you go deeper and deeper down the layers, this signal is changing exponentially. Now, the exploding gradient is perhaps not such a big problem because there's an easy solution to sort of cap it. So if it goes above a certain value, you just cap it at that value, so you can quickly go around this problem. But the vanishing gradient problem was a very severe one, because basically what I told you, that if you're if your network was deep enough, this signal that is propagating backwards to the network that does the actual learning, that changes the parameters, it was never reaching all the way to the last layer. And the last layer is important because that is going to produce the initial features that you're going to need for all the layers on top. So eventually, if we keep adding layers like that, this training signal will never reach all the way to the end, so the bottom layers will learn nothing at the end of the day. And out of this insight from Hochreiter's research, they came up with these long short-term memories. We call them LSTMs for short, to basically get around this, this fundamental deep learning problem. And the LSTMs, they are a recurrent neural network. So unlike the convolutional neural networks, there's feedback connections through the network. So the problem now with feedback connections is that you don't have this beginning and end, so you can go forward and backward through your network. Everything sort of loops around, so you keep going forever. And the traditional way of training that is to unroll these feedback connections and basically create a feed-forward neural network. So you can go forever, obviously, but you can unroll it enough for the learning to happen. So depending on what you're learning, so for example, we use LSTMs at Sensibill for reading text and extracting information from text. So in the case of the text, each sequence would be, say, one character or one word. So in order to learn patterns in the text, you might have thousands of characters long patterns. And the problem is that if you try to unroll this thousands of characters, you would basically have 1,000 deep neural network. So that's why recurrent neural networks were not successful at all, because you needed to have these hundreds of layers of neurons in order to learn your problem. And because of the vanishing gradient problem, you could only learn basically very short time dependencies. So what they did is, which is shown in that very sort of messy diagram, which is still a simplified version, they added a state to the recurrent unit, and they added these gates around it. So this is why it's called a long short-term memory, because so the output could be interpreted as the short-term memory, and the internal state is the long-term memory. That basically, and you have these gates around it to protect the state from being changed. So this, all these gates, they have learning units in there as well, and basically they learn. So you have an input gate. So the input gate learns how to take the input and incorporate it into the state. The output gate basically learns how to take the state and the current input and produce the output. And a bit later on, there was this forget gate that was added, where basically it learns when to forget the state. So this is useful, for example, when you're reading a pattern and you reach the end of the pattern, so you need to clear your state to get ready, so to speak, for the next pattern. So by adding these gates around it, we are basically we are protecting the state from being written to at any time, which is the case of sort of the standard recurrent nets. So now the backward propagation signal gets preserved through the state across multiple sequences. So basically, this type of neural network has the potential, doesn't have a limitation on how far back it can remember. Because if a pattern is important enough, it can learn to know the beginning of the pattern, incorporate that into the state, and then keep basically reading the input until it sees some end pattern, and then incorporate that into the output. Sorry, I need some water. Right, so long short-term memory is basically are sort of slowly replacing all these different recurrent neural nets. So, for example, Google replaced their the networks that listen to you when you say "Hey Google," all the sound detection. They've been replacing them with LSTMs with really great improvements, being able to slash their error rates by half. So, to talk a little bit about the deep learning that we do at Sensibill, so we use this long short-term memories to read the text on receipts that people submit to us, and then we want to extract all the different informations from the receipt text. So, for example, what are the items that you bought? What's the grand total? How much taxes did you pay? And like 150 different things that we extract from receipt information. And what we do is we use a character-based model. So instead of feeding words into our model, we feed each character at a time. So most classical techniques work at a word level. So initially, you need to basically transform, come up with a dictionary of words. And depending on what text it is, that can already be challenging. So for example, we're dealing with receipts. There's all kinds of things there that don't fit into sort of standard dictionary. There could be addresses. There could be all kinds of numbers. The text is imperfect. So every word in the dictionary will have several versions with slight mistakes in that. And the classical approach would be to reduce all your words that you see in your data set, reduce them to a smaller set of dictionary, and then out of that, you have a way to transform, to map each word to a vector, and then you'd feed that vector to your recurrent neural net that does the recognition. So what we do with the LSTMs, we feed the input each character at a time. So now we don't have to worry about sort of the size of the dictionary, especially in our conditions. You don't need to do this lemmatization or stemming, which is are some tricks that are used to kind of reduce your dictionary size. So for example, each word can be seen in multiple forms with sort of different endings. It could be the same root word, but it could be a name, an adverb, a verb with slightly different variations. So one of the techniques is to try to reduce every word into its root form, which involves a lot of pre-processing. Usually all the numbers are sort of reduced to a single thing. So we treat all the numbers the same way. But especially in a receipt, numbers are very important. So some numbers are prices, some they are like SKU numbers, street name, street numbers, and so on. So we can't really treat all the numbers the same. By using a character level model, we kind of bypass the whole problem altogether. And what we see, so this is from a paper where they basically try to map the character n-grams of the words. So what we can see is that it's kind of learning a basis of word formation. So here it kind of clustered all the suffixes together, all the prefixes together. So it's not just learning to map words into vector, but it's also learning how word formation. So by using this character level model, it can learn all the slight different variations and flavors of each word. And we don't have to worry about sort of correcting mistakes. So the network, if it sees sort of mistakes in the words, it can learn to sort of ignore the mistake, just like a human would do, where you would read some text with errors in it, but you kind of bypass all the errors altogether. I think this is the end of my presentation. It kind of went a bit fast. So I guess I can reserve some time for questions. I know it's a bit technical, so I apologize for non-technical people. and I'm hoping some of the technical people would get some information out of that. Yes?
We have a microphone, so I'll bring it around.
Just wondering, like, if you, during the training of a system, you kind of mislabeled, so you kind of say, show the image of a, say, 8 digits, but you said labeled is a 7. So kind of the system becomes kind of polluted. Is it possible to detect, to retrain, to kind of, how is it resistant to such kind of errors?
Yeah, so it's very dependent on your training set. If you have what we usually call garbage in, garbage out. So the thing is that this kind of architectures, they can learn anything. So for example, there were some experiments where they would take white noise images and they would label them. And the network will learn in the training set to just label correctly white noise. But if it sees a white noise image that it has never seen before, obviously it doesn't know what to do with it. So if there's inconsistencies in your training set, they're going to get reflected into your output. So part of the challenge with this is basically how to guarantee that your training set is good enough, how to efficiently label data, and so on. But the advantage is that so before, with this sort of handcrafted designs, if we see some new things that were never seen before, you might need to redesign your system. It's going to take sort of developers to code it, to think through. It's a long process of change. But with this idea is, if we see some new inputs that we've never seen before, we label them, we include them in the training set, and then we train the whole thing all together. So once you have it set up, it's faster development time.
Okay. Any more? So the question was if he can give examples of some usage of Sensibill in this.
Yeah. So if you're for example a client with Scotiabank, in your banking app, there's this tab called Receipts. And once you go into Receipts, that's basically supported by Sensibill, which allows you to take a picture of your receipt, and then the picture gets sent to our servers. Then we read all the content, all the information that's in it, and then we'll present that back to you in a digital form with higher level information. So this is basically our first product, and obviously like a second tier would be to do something with all this high level data that it's very valuable. So currently we're just offering this service of basically being able to store your receipts and digitize them and extract the high level information and offering back to you so you can sort of track your spending. You can basically use those for your records, want to know how much you spend on coffee and so on, this kind of things.
Okay, so we can take one more? Or two more?
Yeah, thank you very much for your presentation. I have one question. At Sensibill, do you do anything related to time series data analytics using incremental learning?
I'm not.
If you have like electronic transaction, not a receipt or something bill, so I want to do incremental learning on streaming data, like time series data online.
Right, so we don't do that currently, but these algorithms can apply the same way. So in a way, we treat the whole text as a time series, as a sequence of characters.
Yeah.
So the algorithm doesn't really have any information about receipts. It just learns everything from scratch. So you can replace the text with any other time series, and you'll be able to learn that in the same way.
Yeah. And if you have some sort of mismatch between testing data and training data, do you do some sort of domain adaptation, or you have to retrain the model?
So usually, if you have a model that's trained on different data sets, usually if your data set is big enough, it's better to train your whole model on the whole data set and then only retrain the last layer. So basically, all these features, so for example, for images, what they call it transfer learning. So you first learn your neural network on all your objects to recognize all objects. Now, if you want to train a model that just recognizes specific breeds of dogs that are sort of very domain specific, you don't train the whole system, so you reuse the whole features that you learned through all objects, and you just train the last fully connected layer, that perceptron layer, to basically recognize between all the different types of dogs or all the different kinds of fruit and so on.
Thank you.
Okay, so one more.
So if to your API, if I instead of giving it a receipt, if I gave it a poster, what will happen?
A poster?
Yeah, like any random image which has text in it, then what will happen?
So I guess we're only trained it in this context of receipts, so it's hard to predict how the networks are going to interpolate. If you have sort of receipt-looking things, it's probably going to pick them up. So if you have sort of numbers that look like prices, it might try to pick those up. If you have sort of addresses looking like addresses, but it's really hard to predict in sort of an outside-the-box scenario of what the network is going to do.
Okay, so because we have another speaker, we'll end up with the questions now. But what if anybody has more to find out about Sensibill? Where can they go?
They can go to getsensibill.com.
There you go. Anyway, if you are on our meetup, we'll send the presentation and all the details about our speakers, so you can contact them or their companies and maybe buy some products from them. So, okay, thank you very much, Julian.
Thanks.
Yes, please, you were saying something.
Oh, I was just saying, currently we only deal with banks, but eventually we might open our API so you can start playing around with that.
So if you want to work with Sensibill, you have to open a bank.
Yes.
Okay, so thank you again.